Alright, welcome back. We are Game 2005 in the Fall 2020 semester at George Brown, and it's Game Physics, and it's week 13. Alright, let's talk about where we are. We're sitting at week 13, 3D collision and response. We're also going to talk just a little bit of 3D collisions, not just the detection, but the response part as well. Last week I gave you assignment 4, and I need to clarify some parts about this today, so that's part of what we're doing today. Next week it says special topics. Chances are what I'm going to be doing is working with particle systems, and or I'll talk about more of a character controller probably around next week, how to do that properly, maybe share some scripts and all that kind of stuff with you. Alright, so what are we doing today? So a quick review of 3D collision detection. We need to talk about that just briefly. I also wanted to bring it into this PowerPoint just to make sure that we had it close at hand for some of the equations that we're going to need today to make work. Okay, so that's kind of where we have that right now. As well, I want to talk about collision response and what that, there's some complications around this. We're also going to be talking about something called the collision manifold. Really, if you think about this, is like a manifest, if you will, of all the contact points that can possibly come up when you have 3D objects colliding, and the idea of impulse. So not just momentum, but impulse. And we'll talk about what the difference is between impulse and momentum. You should know what this is. And then we'll do a short Unity demo, but again, my recommendation is you work with Spencer on Tuesdays, and hopefully he can help you, kind of guide you and, provide a bit of a catalyst to make it easier for you to learn Unity. And again, there's several recommended resources out there that I've talked about for Unity. I don't expect you guys to be experts by any means, but what it's supposed to do is it's supposed to replace our 3D framework. So from at least from one perspective, it should be quote unquote easier than what it would be if you're using something like OpenGL. Okay, so that's the idea behind it. Again, this might be different next time we do this course, but for this course, it's Unity. Let's talk about a little bit about 3D collision detection revisited, just one more time. And I'm going to use some of these equations today. So again, sorry, just like with 2D collision, we work, an axis-aligned bounding box is probably the most common collision detection collision shape, if you will. It's easy because we just need to take its extents and wrap it around. We can use it as a bounding volume around any kind of object, okay? Whether it's a regular, a box, or even something that looks like this, which is a sphere. Doesn't matter, all right? As long as we wrap it around, we can use our basic collision detection techniques to detect if there's an overlap, which is the thing that we're doing. So that's kind of what we're talking about. So from a performance perspective, that's why we use it. Non-rotated boxes in 3D, you can modify them to make it so that they're more accurate. Again, they're not going to be perfect, but you can do something like this where you can take more or less an object, even if it's rotating, and you can switch around or in real time adjust its bounding volume. Again, this is less computationally expensive than trying to use something like a bounding volume that would be object oriented. So an OOBB or an OBB, object oriented bounding box or bounding volume. Okay, so this is a little easier than that. So I recommend it for this for our assignment. Remember, our assignment does not require any kind of angular momentum. I'm not looking for that. Any kind of rotation. It doesn't have to be super realistic, guys. Remember, this is still foundational stuff. In the next course you're going to do, which is going to be more intense than this one, you're going to build on the foundational stuff that we've talked about in this course to create more of a realistic physics engine. Okay, this is not what we're doing this semester. All right, so I wanted to put these equations out for you. So again, point AABB, a very common foundational collision detection method. Why? Because points can be representing vertices. Points can be representing rays, the end of a line segment, as an example. So this is definitely something that is foundational, and we can use an equation or some kind of function that might look like this, okay, where we have a point and we have a box, and the box would have extents, minimum and maximum extents, and from there what we can do with it is we can compare the point, and if it's within the extents of the box, you have a collision. So this is definitely a foundational piece. The other point we talked about last time was AABB versus AABB. We're going to do this today. One of the things we're going to try and do today is at least get some kind of collision detection going in Unity. All right, so we're going to try and do this where we have minimum and maximums. So again, extents of the box. Notice that there are, even though there's an A, we have A and B, we want to have two boxes, A and B. Both only have two extents, a min and a max. Okay, so this is kind of something that we have to look at, right? And also notice that they have things like, you can break min and max down. Notice that in this case, the boxes have min x, min y. So there's like a bunch of different mins, not just a set of mins, a vector 3, but not necessarily that, but rather the maximum and the minimums on all sides. Okay, so this is kind of something that we want to talk about. So this is kind of the equation we're going to be using today. Okay, at least this one. The other one is point versus sphere, another foundational way of doing stuff. This also uses square root, and what we want to do here is, again, we want to replace square root because it's computationally expensive to do this every single time. We want to use square magnitude, which is better, right? Square magnitude and square radius, which we can replace in the equation, but for the most part, this kind of thing is what we're going to be doing. Okay, so that's that. And the other one is sphere versus sphere. We're also going to try and do this today if we have time. I'm not sure we're going to have to do we're going to have time for this, but it'd be nice to be able to do sphere versus sphere today. Okay, it's all depending on how the flow of this this presentation is going to go, and questions that I may get from you guys. Again, you want to calculate the distance, and you want to just check to see if the distance is less than the square of the radii. All right, that's what you want to try and do. Okay, so that's what or the radii added together is what I'm saying. It's from radius from one object and radius from the other object. Okay, so that's kind of what we got there. Sphere versus AABB, also something it would be nice to kind of combine, because if once we have sphere and AABBs, well then we can cover a lot of things with those two objects. Remember that a sphere doesn't care about the orientation of the thing inside of it, and that's why for most basic physics systems, a sphere in three-dimensional space is the easiest way of detecting collisions. Easier than AABB because, although maybe not as accurate, logically, it's hard. It'd be really, really hard for you to see it, the logical collision versus the visual collision. That's really difficult to see in 3D, so spheres are used a lot, okay? The other thing is sphere versus AABB is also a foundational collision detection methodology. Why? Because we can use part of a sphere for the bottom part of a player character, right, where they touch the ground, as an example, and AABB for the plane that we want to surround. And typically, it's much easier for us to define a plane. So, the extents, again, we get the box extents, and we get the sphere. And once we have these objects kind of defined, sphere and box, then once we've got that, we can work out this equation, and it shouldn't be difficult. Again, this is using square root, but we can replace square root with square magnitude and squared radius. Okay, so that's kind of what we're talking about today. So detection is one part. Also, when we get into more complex things, we talk about something called bounding volumes and bounding volume hierarchies. So what if you have a tank, as an example, in 3D, and the tank has a turret? So example would be the tank itself would be the entire object. This would be the entire entity. the entire entity would include the tank body as well as the tank turret. Okay, so two different sub-objects, if you will, right? Or you can represent this different ways. These are bounding volume hierarchies where you can see that there's sub-objects inside of a larger object. And this is a simple example. Okay, tank has the bounding volume. You might have a gun that is one part, there's another part that's in here, so a gun. You have the turret, which is another thing, and it's all inside of the tank object. Okay? Then we might have more complex bounding volumes. For example, if we had, let's say, a three-dimensional mech warrior of some kind, right? Where you might have the head, and you might have the chest and another bounding volume. Notice that we're using spheres here, right, to encapsulate some of these areas, but this is a much more complex bounding hierarchy. Why? You have many more regions that you have to check for, okay? So that's why. And if I have to check all these regions, remember, I'm checking each collision area separately every frame. The more complex the bounding hierarchy, the more times I'm making checks, the slower and less responsive my entire system is going to be. Okay, just letting you know. Again, this is pretty straightforward logically, but I wanted to talk about this before we get into collision response techniques. When we think about a collision engine, if we're going to make a collision engine, we have our update function, some kind of update, and then there's a few stages of collision detection and response. Okay, so here's the collision system stages. Some kind of sweep and prune, where we process the bounding volume hierarchies and other approximations. So what are they? All right, next, first part. Second is, do I have object collisions happening? All right, that's the second stage. And the third stage is, okay, now that I have collision detection, I've detected collision, what do I do? I need to respond to that collision. And there's some things we can do here. For example, the idea of I want to correct any interpenetrations that we talked about before, or any deformity when it comes to geometry. If we have some kind of deformable objects that are not rigid bodies, there's some kind of soft bodies. What do we do with those, right? Or if I have a rigid body that I want to replace with a destructible body, something else that, seems like I'm going to respond to what happens anyway, all right? So those are the kind of things we do when we build a collision engine. All right, so any questions around this stuff? So this is kind of like a precursor or a preamble. We've talked about this stuff before in terms of collision detection. We've done it in 2D, we've expanded it to 3D, and I'm just revising it again for you just to refresh your minds when we move into this next part. All right, collision response. So again, when it comes to 3D games, we got to think about a few things that can be problems for us to work out. Okay, one problem is detect the interpenetration and model contact. So sometimes what happens is we may have more than one contact occur at once at the same time, right? And if I want a believable response, I need to get a set of contacts and then respond to those contacts accordingly. If I was going to be super realistic in a simulation kind of thing, okay? The other thing is I want to ensure that my objects react according to believable dynamics. So does it make sense? Especially if I have any kind of rotation or anything like that, it's got to respond in a reasonable way, okay? And then we have to also enforce this idea of non-interpenetration. So if we have interpenetration happening, some kind of overlap, then we have to separate them again. And there's some ways, there's some techniques we talked about over the last couple weeks to do that. So again, when it comes to non-interpenetration, so we have these discrete time steps. Again, there's two different kinds of collision detection if you think about it in 3D. One of them is discrete. So when I have a time step, frame 1, frame 2, frame 3, and I keep going one frame at a time, right? And the other one is continuous detection, and that's going outside of the fixed frame game loop that we're using. And what we're doing instead is we do many more kind of collision detections between frames. So we might have a game frame, we want to run the game at 60 frames per second. As an example, we might be able to run our collision detection at 120 frames per second, right? We're not rendering at the same speed as we're detecting. That's also a possibility. which increase the time that we can respond. We're going to draw something. Now we have to make sure everything is in sync. We can do stuff like that. We can also make it so we can do predictions. That's another way we can do it. So instead of running things in out of sync with each other, out of time step, we can do things with predictions, right? We can predict where something is going to be and do some kind of time travel. And I don't mean like that in science fiction ways. I mean actually predict, make a calculation of where we're going to be next frame, and then do some adjustments. Okay, so. But one thing we also want to detect when we want to be super realistic is this idea of exact collision time. When is the exact time that we collided? Was it before this frame? Yes. When? How much back do I have to go to get to this point? We don't want this interpenetration stuff happening. It doesn't look realistic. We want it to do something like this. Okay? And so what we want to do is we want to do this retroactive detection. So, or also known as backtracking. So we want to kind of start at time 0. We're heading down, as an example, with a particular particle. The particle is penetrating inside of a surface. It could be a plane or the surface of the bounding area of a box or something else, other geometry. And as it penetrates, you know, especially if it's going very fast, the tunneling effect could take hold and it could maybe go right through. We need to reposition this so that it appears realistic, right? And again, put it outside of the bounding area. So this backtracking stuff is what we need to do, which means we need to keep track of what's happening if we want super realistic motion. Okay? Let's talk about manifolds and impulses. So again, in order for us to respond to collisions, we need to know more about what they are and what has happened. And so what we do is we develop something like a collision manifold, which basically holds the information about my collision for each of my objects. Okay? And then what we want to do is create manifolds. We build, once we create them, we build a linear impulse system, all right, to learn the basics of collision resolution. And that's what we want to do. Okay? Because, again, notice that I said linear impulse system, not angular, no torque. Okay, I'm not even talking about those kind of things, because once we start getting into that, it becomes way more difficult. Then the level of challenge goes up a lot, right? So we're not going to handle that this semester. However, there could be, I think there's value in further exploring that for yourself if you're interested in super realistic physics engines. The idea here is that you understand the basics of how things work. Okay, so manifold for spheres. So again, what we want to do is we want to get some information about when it comes to sphere collisions, sphere type collisions. We always want to know about the collision normal. Okay, we want to know about the penetration distance. So when we have a collision happen, this is what we're talking about. That's what a collision manifold is. We have a collision happen. We need to know what's the angle of the collision. When did the collision occur? Where did it occur? And what's the angle of attack, if you will, right? Or what we talked about, which is the collision normal, right? Where did it occur and at what angle, okay? Some kind of penetration distance we want to calculate, and a set of contact points, okay, if we're going to be able to respond to the collision, all right? And additionally, we want to be able to have references to the colliding objects, so we have to know what the objects collided were and the reference to the entire object itself. Something called relative velocity of the collision, the whole collision system, and then the kind of collision, the nature of collision. Did we have a collision? You know, are we still colliding? Are we penetrating? What kind of collision detection is occurring? Okay. So let's assume we have two colliding spheres, A and B, and then the collision normal of the manifold. So this is the collision itself. Think about the manifold as the system, the collision system that we're looking at for those two spheres colliding, as an example. It tells us the direction that each object needs to move to resolve the collision. So where am I going to go with the collision for each sphere, right? After we're done. After we resolve the collision, we've hit something. Now what do we do, right? A good example is if A moves in the negative direction of the normal and B moves in the positive direction of the normal, the objects will no longer intersect afterwards. Okay, so they're going to go in different directions. Okay. One thing also we're talking about here is something called the penetration distance of the manifold, right? Which is half of the total length of the penetration. All right, so when I go completely through, right, why is it half the length? Because remember, the penetration is both sphere A and sphere B. We're going to have an overlap, right? And that overlap is going to be, we're going to separate that, the total distance, we're going to divide it in half, and that is the total penetration distance that we want, which is the length of the penetration. Each object needs to move by the penetration distance to resolve the collision. So remember, penetration distance is not the total penetration distance, like not the total overlap, but only half of the overlap. Why? And half per object, because this way I can move one object out exactly where I need to, and the other object back exactly where I need to, especially when you have two objects that are moving, you know, so that way we have a kind of realistic collision detection and response. Okay. Finally, we need to get this idea of a set of contact points in the manifold, which is all the points that the two objects collide with, right? Because you're going to maybe have more than a bunch of vertices that kind of overlap. Okay, so contact points. Okay. So here's an example of that. Let's suppose we have two spheres, right? And we have another sphere here. Really, the nice thing about spheres is they only have a single contact point between them, right? Because, right, at the end of the day, we're going to have one spot, because spheres are the way they are. We're going to reposition them, and when they're repositioned, when they're connecting on a single vertex, whatever that is, right? That's what's going to happen, where it's a little different when it comes to other kinds of objects. Okay? And again, the collision normal is something we want to kind of track. I want to know, you know, the collision, and how do we find the collision normal, I think, is the other thing we want to think about. So we want to find the combined radius. The first thing we want to do is, like, let's find the combined radius of the spheres, as well as a vector that points from sphere A to sphere B. And this should normally be normalized. Why? Because we don't need the magnitude, the vector, to have a full magnitude between A and B, but rather it's just pointing from A to B. Okay? And once we have that, we want to find the contact point. And what we want to do is we want to move from A to B along the normal, right, by the penetration depth, and we're going to find the point of contact that way. Okay, so example would be the magnitude of position A and position B. There's a magnitude, so a distance between the two from centers, right? And what we're going to do is we're going to subtract the radius of A and the radius of B to find that contact point. Okay, that's what we want to find. That's the point of contact, because we're going to move back to that point of contact along the collision normal. Okay, that's what we're going to do. Now, here's the wonderful thing about Unity. Unity has a great math library that we can use, and we can automatically detect certain things. All right. Now, again, this is not using collision detection or the built-in physics system. Okay, we're not doing that. So remember, for assignment 4, you are not allowed to use any built-in collision detection or physics. Not for gravity, not for motion, not for detection, none of that stuff. You have to make it all yourself. Okay? So we need to create some structures, because we don't have any structures right now in Unity. We have some of those things in SDL, but we need to make some of those structures in Unity in order for us to do collision detection and response. All right. So it's different when it comes to an object-oriented bounding box and a sphere. Now remember, we talked about object-oriented or oriented bounding boxes, OBB, and spheres are very challenging. But I want to talk about them because it's quite normal in a real physics engine to have this situation happen. We're not going to do it, of course. We're going to try and stick with axis-aligned bounding boxes because it's easier, not because it's better. Okay? So what we want to do is we're going to try and figure out the closest point on the OOBB. Actually, it's the same thing when it comes to detecting AABB and Sphere. If we're looking at the closest point, which is not necessarily a vertex. Okay, it could be some other closest point. Okay, on the actual surface of the OBB. If the distance from the center of the sphere to the closest point is greater than the radius of the sphere, or if we can't find a normal vector, there is no collision. So we can't find a normal, we don't have it. If there's a collision, the normal of the collision is a vector that points from the center of the closest point on the OOBB to the center of the sphere. All right, that's how it goes. So it's pretty simple. And what we want to do is we want to find the distance between the closest point on the surface of the sphere and the closest point on the OBB. Here's an example of what that would look like. So we have some kind of rotated box. Okay, this is not an AABB, but an OBB. Okay, and we want to find the closest point to the center of the sphere. That's what we want to find. A lot of times what we want to use when it comes to OBBs, because it's very difficult, like it says here, the collision normal and penetration distance come right from the separating axis theorem. So if we're going to use, usually what we want to try and do with OBBs is use SAT, because SAT is more accurate. The challenge with SAT is, especially in 3D, in 2D it was challenging, but in 3D there are 15 axes of potential separation between two OBBs. Okay? So when we think about it, these are different kinds of possibilities. We have point and face, edge and face, edge and edge, edge and face and face, and a bunch of different ones. So lots and lots of different possibilities. And this is where, and we're going to see that if we're going to develop a system, right? If we were hoping to develop a system like this, then we would have to deal with each of these cases across every normal. If you think about it. So remember, this is just on one side, right, that we're talking about it. What about on the bottom? What about on the top? Anywhere that this can happen on different places. That's why you have many, many points of contact that are possible in three-dimensional space. Okay. And this is why we're sticking to kind of simplified collision detection is what I'm asking for in your assignment 4. Okay. All right, again, we would want to get a contact set, a set of all points, and a lot of times to make this easier is we might get duplicates, and we'd sort through all the duplicate points there because we don't care, right? And we would reduce those points to kind of individuals, but we don't care. The contact set we would use would be good enough to understand what points of contact we'd have for each of the objects, and once we have that, we'd get the closest point, whatever that is. And that is we're going to calculate the collision normal from there. Okay, so same kind of idea. All right, so that would be how we would do it if we were going to do OOBB or OBB, right? We're going to be trying ABB or AABB, axis line bounding box, right? And we need to resolve our collisions using something called impulse. And remember, an impulse is an instantaneous change in velocity. All right, so it's we have something that happens. We're going in a particular direction, and when we instantaneously change to a different direction. Okay, we're not talking velocity changes from 1 necessarily to 1.1. We're not talking about that, although that could be considered an impulse as well. We're talking normally in terms of it's going to go to 0 or it's going to go to a negative, right? So it's instantaneous change. Something's going to cause it to happen, the collision, right? And that instantaneous change we call impulse. So what we're going to try and do is linear impulse, where we don't care about angular momentum. We're not caring about linear torque, impulse torque, which is we're not looking at that at all. We're just looking at impulse on a linear scale, linear line, like one line, okay? So when two objects intersect, we will find the collision manifold between the objects first. So what contact points, what's the normal, all those kind of things. And try and figure out what impulse will resolve the collision. So we're going to figure out this impulse. And again, the impulse is a velocity. All right. So again, we might have an impulse on box A to resolve the collision. That's different from an impulse on box B. Why? Because box A and B might be of different masses, right? Might be of different masses. Once we have the features of the collision, whatever those are, we can apply a linear impulse to the colliding objects to solve the collision. So first we get the manifest or the manifold. What is it? Give me features of the collision. Contact points, the collision normal, the relative velocity we're going to talk about in a second, and a bunch of all these things. Once we know these things, then we can apply them and we can resolve the collision. The other thing we also have to think about is friction. I talked about in the in your assignment 4 that what if you have these piles of boxes as an example and we have friction, right? So that is going to provide another type of impulse, right? But instead of an impulse being along the collision normal, right, it's going to be tangent to the normal, which we're going to talk about in a sec. So here's some examples of this. Sometimes what we want to find, actually most of the time, is we want to find this idea of relative velocity of the system. So let's get relative velocity of these two objects. Why? Once I find the relative velocity, right? Example, an object is moving at 10 meters per second. Another object is moving at 20 meters per second. The relative in the same direction. The relative velocity is 10 meters per second. That's the relative velocity. So we take the original one object and velocity and subtract it from the other object to get this relative velocity. Why? Once we've done this, we normalize the velocity. So when we have a normalized velocity, I can deal with one number and not two, which makes it resolves a lot of problems in my equations, right? When it comes to trying to figure out what to do, I have a relative velocity. Once I have a velocity, just going back to 2D static collisions, I have a velocity I can reflect. If I'm hitting a wall or an object, I can assume that one object, we're going to make some assumptions, that one object is static relative to the other one. A good example of that is, let's say, for example, I have object A. It's moving at 10 meters per second or 10 units per second in the game world. And I have object B. It's moving at 20 units per second. It's the one that's moving. The other one, we can assume, is standing still. Once we can do that, once in our mind, if we can model one object being static and the other object being dynamic or moving, we can apply the same rules of motion that we've been using all semester, right? The same kind of motion and response. Okay? All right. So we've found relative velocity, and then what we want to do is we want to know the magnitude of the relative velocity. Again, relative velocity is going to give us a direction, right? And we also want to know, because the vector is both direction and magnitude, right? We want to get that. And that direction or that magnitude is going to be along the collision normal. The collision normal is we're going to calculate the collision normal based on the relative velocity, right? If the magnitude is greater than 0, then the objects are moving away from each other and we can't apply any impulse, right? So that's something to note as well, the magnitude of the relative velocity. We find the magnitude by taking the dot product. So this magnitude that we're talking about is a different magnitude than the length of the vector. We're not looking at that, okay? We're looking at the, we're calling it magnitude, but really what it is the dot product of the relative velocity and the relative normal. And the relative normal is just the collision normal. So if I have the collision normal, I know where I'm coming from. Almost like, think about this as the angle of attack as an example, right? So an object is coming inbound at a specific trajectory, right? It's going to hit another object. That is going to be the collision normal, the angle that the object is moving in. Right? Once we have that collision normal, we multiply it by the relative velocity, or we don't multiply it, we use a dot product, and now we have something called the magnitude of the relative velocity. And once we have the magnitude, we can do other things with it. Okay, again, these are all little steps to help you calculate more accurately collision response. One thing we also have to know is something called bounciness. And bounciness is a very, kind of a layman's term for things when it comes to elastic collisions. And what we normally use is something called the coefficient of restitution. All right, so, and actually, and even in Unity, in their physics system, they use something called restitution, where when in our mind we think about it as bounciness. Okay, so it's in our model, it's going to be represented by E. We're going to use E for the coefficient of restitution in our formula. And what we want is both objects involved in the collision have this restitution, and we will use the smaller value as the coefficient for the collision. So example, we might have, if I want to find the entire system, we're talking about two objects colliding, right? Object A and object B. Let's suppose both of them have some kind of bounciness. One is, let's say, a brick. The other one is a ball, right? The ball might have a much higher coefficient of restitution, right, than the brick. The brick would have a much lower coefficient of restitution, right? So we want to take the minimum of those two things to provide the coefficient of restitution of the system that we're talking about here, right? Both objects colliding. And that coefficient of restitution we're going to use in our formula to see how much they bounce back, how fast they bounce back, what is the momentum or impulse that's going to be driven back across the collision normal, all right? So when we take the magnitude of the velocity of an object, right, after the collision is the same as the magnitude of the velocity before the collision. Again, this goes back to the idea of conservation of momentum, right? And it's going to be scaled, and this is kind of what we talked about actually earlier with your assignment number 3. It'll be scaled by the coefficient of restitution. So example, if you made a very bouncy wall in assignment 3 for the second part where it bounces off the wall, if it was bouncy, then it's going to provide additional, energy, if you will. It's going to provide energy to the system or transfer energy because of the bounce, right? Think about the coefficient of restitution as a spring force, right? Where the coefficient of restitution has a potential energy that's inside of it. The more springy the wall, the more energy that's going to be transferred to the system, okay? So here, if we want to find the magnitude of the final velocity, right? The magnitude of the final velocity of an object is equal to the relative velocity, right? Times or dotted with the collision normal and multiplied by a negative coefficient of restitution for the system. That's going to be your final velocity, the magnitude of the velocity. Okay, that's how it works. Again, I'm stating these things because you can create, from these formulas, you can create any kind of code you want, right, to simulate what this is going to do. So we use negative coefficient of restitution because after the collision, V prime, right, is pointing in the opposite direction of where it was going before, right? It's going to go in the other way, right? And the magnitude will be used as part of the magnitude of the impulse, J, which we're going to see in the next equation. So again, when we think about impulse, it's like a moment. Impulse and momentum, right? Where momentum is mass times velocity. So therefore, if we're going to take the instantaneous change in velocity, that's the impulse for that particular mass, right? So velocity equals impulse divided by mass if we kind of move things around. And if the magnitude of our impulse J and the direction is n, the collision normal, then the updated velocity of an object is given as this equation down here, which is the final velocity, v prime, is equal to the initial velocity, v, plus the impulse over the mass times the collision normal. Okay, that's what the equation would be. Okay, and we're going to get a good response with this thing because why? We're going across the normal. We're going to have this new velocity vector, which is pretty cool. That looks like pretty crazy, but the thing is, at the end of the day, I mean, if you think about it, it's not that difficult. It's quite simple. There's not a lot of variables here. right, for what it can do. And you should test some of this stuff out when you start experimenting. That's why you have more time for this assignment than you would if for the other ones. We also need to adjust for the coefficient of restitution, because this equation here, doesn't really take that into effect. We don't really care about restitution to figure out the final velocity. Imagine that there is no restitution, there's no bounce, right, as an example. We just kind of slide off as an example. But in order for us to do that, we sub it in. So we sit there and and we also take into account both masses, because now we need to take account both masses of the system in order for us to create the idea of the moment, or the impulse that we want to calculate up here. So this J, remember, is the impulse, right? And once we figure out the impulse, right, we can replace our equation with something that looks a lot different. So for example, if I want to find the final velocity of A, we take the original velocity of A, subtract from the impulse, right, over the mass of A, times the collision normal, whatever that's going to be. And the same thing goes for B. So again, linear impulse, something that you guys should take a look at. And I think it's important, kind of an important concept, the idea of impulse, which is derived from momentum, obviously. Let's also think about friction a little bit, because one of the problems I gave you to solve was, how do I solve for friction? If I have additional friction, it becomes another type of impulse, if you think about it, right? So it's a separate impulse. So we apply something called impulse friction after applying the constraint impulse that keeps objects from penetrating. Constraint impulse would be something like, I want to do that backtracking, that time traveling, where I move an object back outside of the penetrating, interpenetrating kind of situation, where I have an overlap. I don't want to have an overlap, I want to pull them back out to the point of contact. That's the constraint impulse. And then I want to apply the impulse friction after that. Okay, and impulse has let's say this magnitude of J moving in the direction of the collision normal N, and then the friction will be applied in a direction tangent to the normal. All right, tangent to the normal. So that's pretty good, right? And we call this direction T. Okay, and then similarly, the magnitude of the friction will be called JT, where we take the impulse and multiply it by the tangent to the normal. So how do we find the tangent vector? We take the relative velocity and we subtract the relative velocity, the magnitude of the impulse. That's what this is, right? Relative velocity dot with the normal. And then we multiply it by the result by the collision normal. All right, so that's how we find the tangent vector. Right? Once we have the tangent vector, we can actually add it down in here, where we say JT, which is impulse times the tangent vector, is equal to the equation we had before that includes the coefficient of restitution that's up here. Okay, so kind of straightforward. The other thing that you notice is there is T that's also being involved here, where a couple of examples ago there was no T. It was N. Okay, so that's the difference, where we've dragged T out here. Okay, and here what we want to do, we want to try and calculate friction, is we want to get the square root of friction of A plus the square, or with friction of B. Once we have the square root of these two things, then what we want to do is, that's going to be our total friction. Okay? All right. I want to stop there because I've talked about a lot of different things, but this is the general idea. This is the concept between what we're trying to do when it comes to response. The idea of impulse, the idea of collision normal, the idea of retroactive kind of non-penetration, which is called backtracking, like this, retroactive detection. We want to be able to do those kind of things. All the same tricks and things that we've talked about throughout this semester. Okay, that's why it's a kind of a culmination of things that you're doing for the final assignment. All right, any questions around this before we go into the Unity demo? If you do, please put up your hand inside of the participants panel. If not, we're going to move into the Unity demo now. Vincent, talk to me.
Yeah, I'm just trying to go through.
Yeah, I'm just trying to go through.
Just talking about
Just talking
linear
about
impulse. There's
quite a lot.
Yeah, there's a lot of stuff to think about. Yeah.
So for the
we have a normal restitution which is not accounting for friction, where it's J equal to
whatever, and then the dot product
whatever, and then the dot product of the
when you have friction, you have
when you have friction, you have the dot product of the relative
You got it.
velocity
Yeah.
to
Yeah. T would be which would be the tangential tangent to the normal, to the collision normal, right? And again, you'd find that tangent if we're going to do it. You'd find the tangent when it comes down to this. This is the equation to find the tangent to the normal, right? So take your relative velocity minus the magnitude of the collision normal. That's what this is. Magnitude of the impulse, actually, and then multiply by the collision normal. And then once you have this, then you've got the new tangent vector. And that tangent vector is what you include here. You multiply it by the impulse, and then or JT is really the new impulse, right? And you can find JT by doing this. Okay. Again, I know it's a bit of convoluted stuff, but at the end of the day, we can make it simple, right? We can we can puzzle it out as well. Think of it this way: our friction, right, is really going to slow down. It's going to be kind of the opposite to the restitution. So if I have a high amount of restitution, so a lot of bounce, right?
Yes.
Then I'm gonna transfer energy from across the the system boundary from one object to the other, and it's going to be more energy transferred as a result of the bounce. The higher the coefficient of restitution, the more energy, almost like a factor. Think about it as transferring a bounciness back out. Instead of reducing reducing the energy, I'm adding to the energy for bouncing, right? That's what I'm doing. Again, so minus other things, so right? Whereas the friction is reducing the bounciness in some ways, reducing the energy. The more friction I have, the less energy is going to be transferred across the system boundary, right? Because the friction is going to be constraining the object from moving, right?
Okay.
So they work against each other.
Okay.
So I have a high friction, which means it's not going to move. But I can have both. I can have a very high friction and a high bounciness, which means it will bounce, but it won't shift, right? Again, in our example, it won't matter, right? But if you're shifting things across a surface, right, then let's say, for example, I'm moving things across a plane, and if I have a large amount of friction, remember how friction works? There's two types of friction: static friction and kinetic friction, right? So we can use those concepts as well to simplify our problem, because this is more complex, right? We're talking about collision detection on the moment, right? Whereas if you have something that's happening where I'm continuously, colliding, because when I have an object on a surface, there's continuous collision detection,
right,
all the time, right? It's happening, and if I'm in contact, then I can't move through the object. I'm not going to move down. I can slide across if there's zero friction, or if there's friction, it's going to slow me down from sliding across. Okay, that's what's going to happen. So again, these are all things you have to consider when you put together something called this collision manifold, which is almost like you have to keep track of almost like the properties or the features of your collision when it occurs. We don't care so much about that in 2D because 2D is a much more simple problem. Here in 3D, we have a lot of different things to think about.
Right.
So that's why it's more challenging than you think. When you start thinking about it, you're like, hey, it's no problem. We can just do the same things as we did in 2D. Yes, for the most part you can, but if you want to make it realistic, then there's some other things to consider. And that's all I'm saying here. Because you already have the idea between collision response, right? The same ideas in 2D you can transfer to 3D. It's just here what they're doing is they're trying to give you trying to think about all the different things. And the normal, the collision normal, because it's in 3D, it provides more information than our angle of attack idea that we had in 2D.
Yeah.
Yeah.
I know.
It's a lot. It's really a lot.
It's a
I know.
lot.
I
It's
know.
really a
I know.
lot
That's
to,
why
like, absorb here.
we're going to focus on it together. And I'm not trying to complicate it. It's just part of what we do when we do 3D, and that's why when a lot of times we make an engine, a game engine, our physics engine has been made by somebody else, right? Because they deal with that. They're going to deal with making it more realistic and so on. All right. Any other questions from anyone else? Thank you, Vincent. I appreciate that. Okay. So let's move into the Unity demo. So what I've got is up online. I've put together a. I'm just going to bring down this. This is up online for you to download. The link is up on Blackboard, which is if you go to George Brown College on GitHub /GAME2005 F2020 lesson 13. There is this little starter. It doesn't include much, all right, but I wanted to start with something, right, for you to go with, as opposed to nothing, to get us going. It comes with a gitignore file and some other stuff. All right, so let's recap what we did last week. And I'm going to bring up my project. You're going to see a project when you start off that looks like this. And I'm going to talk about how I did this and everything else and what this is all about. Hopefully, Spencer had a good kind of lab with you guys and discussed how most of this stuff works. Okay, so we talked about Unity as a game engine last week. We talked about different components in the hierarchy. So here we have a main camera. Our main camera, if I double click on it, or if I press F to frame select, right, it's going to take me to the three-dimensional object. You can turn off the 3D icon by going up to where it says gizmos and unchecking 3D icons. If you did that, then you're not going to see the 3D icon as big. It's going to be much smaller here. There it is. That's the camera. So if we zoom in, again, we're just using fly-through controls. I'm right-clicking on my mouse, and then what I'm doing is I'm using my fly-through controls. E would also move me up, and Q moves me down to fly closer to the camera frustum, which is what this is looking at right now. This camera frustum, you can see when I click on the camera that I see a preview of what the camera looks at right down here, right? Right now what I've done is I've included a cube inside the scene. Okay, so here's my cube. I'm just going to move closer to it so you can see it. The cube has these weird lines on it, but when I look in the game, I don't see them. Why? I've added some debug gizmos that you can see inside of the debug window that are not visible on the game side when you play the game. These are going to help us do some debugging, okay? And I want to talk about how this works. So, we talked last week about all game objects having certain things. Let me just remove the cube for a second and we'll put it back together, all right? So we talked about all game objects having a transform component in Unity, and they have other components in Unity that make them do what they're supposed to do. We also defined a style of doing things here in our scene. So notice I'm using a tall kind of layout, which I recommend for you. And I'm also waiting, by the way, for you guys to catch up if you've just downloaded everything so you can be with where I am. By the way, let me just see this. Are you with me? Check mark if you're with me, X if you're not. Because that's important to know. So Chris is with me. I got some Andrew, Juan. Yay. Awesome. Agar and again. Okay, good. All right, thank you for that response. So if you're with me here now, we talked about several folders in my assets folder. So I renamed it scenes and scripts. I'm going to add some additional things. Let's make some other things, like for example a models folder. If I want to have additional models that I want to bring in from Blender or something else like that, I can put it in there. I may have some textures, right, again. where I might have something that I want to wrap around the model, all right, as well as maybe some materials, right, which really represent our, combining our texture with our shader, so we can create a material that we can apply to the model itself. All right, so those are the things. Now notice they're empty because we don't have anything in there. Okay. One thing to note, and this is part of your requirement, right, is you cannot have any physics from the Unity side working. All right, so if you're running Unity and you add a shape, by default it's going to give you a collider. Remove it, please. I will not allow any colliders or anything like that to happen that that are not your own. If you've not developed the collider, then it's not something you can use. And that means we need to be inventive in terms of how we do collision detection and response and the kind of naming convention we're going to use. Okay, because we can't use Unity's collision detection system or physics. Suppose that it's not working, right? That means you can't use anything to do with physics or collider or collision or anything like that. No raycasts, none of that are allowed. All right. All right. So if I add an object like a cube, let's add a cube first. So 3D object. I got that by right-clicking, 3D object, cube. There it is. And notice by default, I've just got a cube. I can see its bounding areas. By the way, on the left where it says shaded, you can choose shaded wireframe only, if I only want to see the wireframe, or shaded wireframe, right, which gives us more information when we're looking at an object. The shaded wireframe also shows us its face quads, right? So these are face quads and triangles. Because remember that really at the end of the day, you're going to have two triangles for each quad, right? And it can show you where those are made because each face is a mesh, right? When we make a cube, it's actually made up of 6 faces, right? And each face has it's really a quad. 6 quads is what it is. So we can do that on the scene. So scene will allow us to turn that on. We can also do other things here. If you notice, there's shadow cascades, render paths, and many, many other things that are available to us here on the left-hand side. We care about only these 3. For now, let's leave it as shaded. Okay? Cool. So we have this shaded object, but I want to detect where my extents are. Well, we don't really have a notion of what a cube is right now. We have no idea that this is a cube, right? All we know is we have a game object. The game object has a mesh that is a cube mesh. That's what we know. We also know that we have a mesh renderer. The mesh renderer draws our object. So if I check this component on and off, we can turn off the ability for us to see the cube. Okay? This is pretty cool. The material that we get is a default material. That's why it's colored the way it is. We can make our own color, which we will, right? It also either receives shadows and casts shadows. For now, what I want to do with this cube is I don't want either. I don't want it complicating the scene, right, for us to detect stuff. So let's remove receive shadows, and let's remove cast shadows. So we're going to remove those things. So lighting, how the mesh renderer is going to affect the scene, it's not going to either receive nor send shadows out from a lighting. The next part is down in here where it says box collider. This is what you need to remove from every object you have in your scene. You cannot add an object with a box collider because then you have automatic collision detection. We don't want those kind of things happening for us. So we want to remove this. No box collider, no trigger collider, none of that stuff. Let's get rid of it. So go to the ellipses and go remove component. Now there's no collision detection that is built into Unity. Are you with me? Check if you're with me, X if you're not. Vincent, I see your hand.
Yeah, I unzipped the package from GitHub. I have this error that said the window tried to begin rendering while something else had not finished rendering, or either rendering or the previous ongruity rendering or the previous ongruity.
That's weird.
I don't know if that's an error from my side, or if it was something with the download.
Did you unzip it properly? Did you remove it from your thing? Because a lot of times what happens.
I'm sorry?
Did you unzip it properly?
I'm sorry? Yeah, I downloaded the zip from the GitHub.
I downloaded the zip from the GitHub.
Unzipped it from my downloads.
Unzipped it from my downloads. I placed it in my lesson 13,
Unity Hub,
and then from Unity Hub,
Okay,
from
so
Unity Hub, I was
so let's just here's what I recommend. Instead of going through this problem, again, there's nothing here in the scene. So start a brand new project if you want. My starter just included a bit of a script, but I'm going to tell you the script anyway. So just for if it's easier for you to do it, I'm not going to try and figure this out. Just start a brand new project.
Okay.
And after the brand new project is started, you should be able to drag and drop an object. Is your version of Unity different than mine? Is it 2020.1.10?
No, it is 1.10.
No, it is 1.10.
Shouldn't be a problem for you, right? So, but I'm not going to judge what it is. You know, I can't judge what it is. So, the best thing for you to do is just start a brand new project. It's okay, right? I'm not trying to try and fix it. It could be a bug in 2020, right? Let's start a brand new project. There's nothing that I've really put in the scene except for a cube. We can. I just wanted you to start with something as opposed to nothing. But if it's a problem, let's just start a brand new project and add a cube to the scene, and then remove the collider. That's all. That's where we want to start. Let's do that.
Okay. All right then.
Okay. All right then.
Okay then.
Yeah.
I'll just start a fresh.
Yeah, I'll wait for everyone to catch up.
Project.
If you have a problem like that, please just start a brand new project. Get rid of the stuff that's in there, and then all we want to do is add a cube and remove the collider component. Okay.
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 Got it.
Thank you.
Got it.
All right. So when we have that, and if we look at the main camera shows the cube like way far away. So if I look at the game, you can see the cube is way over here, right? We want to make some kind of scene, and let's add another object in here, another cube, but we're going to make it so that the cube is going to be scaled differently to create a floor. Okay, so let's make this cube, we'll call it the player. We can go to the inspector and click onto it once and rename it by typing in whatever we want. Let's call it player. In our materials, let's add a brand new material. So double click inside materials. And what I want to do when I'm in the materials folder, right? So all I've done here is I've renamed this to player. In the materials folder, I'm going to right click and I'm going to go create material. When I create my material, let's call this the green material. It's green. All right. Yay. It's going to be a player object. I want to change the albedo to green. So I'm going to choose in the color picker here, choose a green color and move this object closer to green. Not totally green like this, but somewhere kind of in the middle. So it's kind of a light green or grayish green. I don't know what you want to call it. All right, so now that I've done that, there's my green. Then what I can do is I can go to my player. I can click on the player and drag and drop the green material into where it says materials in the mesh renderer, where the default material is right now. I can just drag and drop it in there like this. Alternatively, let's undo that change. Alternatively, you can click on the little target on the right, and then you can just pick green or search for it here. If I just type in green, it'll come up. Either way, once you're done, if you click X, it's going to allow us to move away from that. This is still too green for me, so I'm going to go back to my green material and I'm going to go into the albedo here and I'm going to reduce the color value even more, right? If I move now, because it's been applied to my game object, wherever I move it, it's going to change my value immediately in the editor. So let's move it towards more and more white. So kind of a very subtle green color like this. Okay. Again, the values that I used looks like 209, 253, 217, 255. Okay, if you wanted to match what I have with what you have. Okay, I mean, again, all I'm doing is framing it so we can see it. Okay, and we know that we've also changed a couple things. Just to recap, we have no shadows, we don't cast, we don't receive. Next, let's make another object. Okay, so again, I'm going to right click and I'm going to add a new 3D object, cube. And this object is going to start off hopefully next to this one, to the one you have right now, If it's overlapping, just change its coordinates so it's next to it. My player cube right now is at some odd values. We can always reset those. There's the reset, 0, 0, 0, right? And we can always reset these to 0, 0, 0. Now they're overlapping. They're on top of each other. Let's move the other cube away by taking one of the handles, doesn't matter which one, and moving it to the right or to the left. So I'm moving it across the Z plane, right? But you can move it across the X plane. It's up to you. Again, if I rotate stuff, I can move it this way. Doesn't matter. All we're doing is moving it so that they're not overlapping. All right, this would be the enemy cube. All right, again, there's no gravity being applied. We want to detect collisions. We want to do a few things here, so let's start by doing simple things. So cube, I'm going to change this to the enemy. This is our enemy cube. Okay, and you know what? Let's make a red color to kind of with our cube. One thing to note is that it comes with a box collider. Let's remove that. Now here's what I could have done. I could have just duplicated this one and changed the material, but I've chosen to do it this way, so just to emphasize the need to remove the collider, as well as take away casting shadows for now. You can use this in your game if you want, shadows, perfectly fine. For now I'm taking them away, so just to simplify things. So I have no shadows as an example, and I have these two objects right here. I'm going to change the material for the enemy to something that's reddish. So I'm going to go right click down here. I'm going to make a new material. So we're going to go to material, and we're going to change it to red, right? Some red material. We're going to go to the albedo again, or albedo. Choose the red area, and then just move our color picker towards the red, just like a slight pink tinge to it, reddish. My numbers for if you want to match mine are 246, 191, 193, 255. Those are the numbers. And now, since we're recording this video, you'll be able to capture this later on if you wanted to recreate what I'm doing. Alright, on the enemy, I'm going to drag and drop the red material onto where it says element 0 in the material section. So grabbing the red material, drag and drop. And now we see a red material and a green material. Wonderful. Right? Now, here's what I want to do. This is going to be the test. I want to be able to detect collision when I overlap. When I do this, I want to be able to detect this collision in real time when I'm playing in the editor. In the editor now, we're not going to see a very good scene. We're going to see these two things like way far away. So a couple of things we can do here is we can move the camera closer, right, as an example, or we can move these things closer to the camera. It's up to you. Me, I'm going to move the camera closer so we can see these. So in order for me to do that, I'm going to click on the camera, and you can see that I can go to the camera frustum, right? And once I do that, I'm going to take, you can see a preview down here. I'm going to take the camera, so I'm going to move it closer to the object so we can see them in much more detail, right here. And I'm also going to move it up a little bit. I'll give you the coordinates in a second, just a little bit. And I'm also going to angle it down, and I'm going to do that by clicking the angle and just rotating it across the x-axis here. So it's going to move down this way so I can see the two objects in finer detail, a little bit closer to what I had before. Okay? There we go. So my coordinates are, if you want to do what I did, for the camera, 0.389, 1.617, and negative 4.852 with a rotation of 9.978 on the x-axis, if you want to copy what I have. So this way you and I have the same looking scene to the most part. The player right now is at 0, 0, 0, and the enemy is at 1.33 on the x-axis only. All right? Shadow on the face from the directional light. Yeah, that's because of the material type. You can choose an unlit material. That's what you would have to choose. So right now what we're using is for each of our materials, notice that our material is standard, right? If you really don't want anything in there, you can choose unlit. If I go to unlit and choose something like, I just want an unlit texture, it's going to go like wacky wild, like nothing, right? Or I can go unlit and I want to go transparent again, and you'd have to put a texture in there, and then it would be unlit. We don't have a texture right now, so let's leave it as our standard. If I go to standard, right? Notice the rendering mode is opaque. You can go cut out, fade. These are all effects of our shader, right? But that's definitely why it looks like that. We can also add an emission value if you really want it. So let's say, for example, I can add an emissive quality to it so that it actually glows. That will take away the shadow as well, right? But I'm not going to do that here. So let's get rid of the emission. I think this is pretty good anyway. Not if it's unlit. If you choose an unlit material, it'll be lit different. It'll look different than something that's lit. This is a lit material. This responds, even though it's not casting shadows or receiving shadows, it's still got this like darker face because of the material type. Let me just shut my door, guys. I'll be right back. There we go. All right. So we have this situation. You should all be with me, but at this point. So what we want to do now is once we have our green material and our red material, if I run the scene, nothing happens. But we're able to see our objects live in the scene now. Okay, that's what you want to see. If I go into the scene when I'm live, I can still attack the object and move it, right? To make it penetrate. And you can see now that they're penetrating in the scene. If I stop the scene, they go back to normal. So this is what we're gonna. This is how we're gonna do the collision detection without any other kind of code. All right, just to be able to detect collision today. All right. So let's define a couple of things, right? If you remember from the PowerPoint slide, in the top here, we had some collision detection things that I brought into place, which is I had this AABB style collision. Well, one thing is, in order for us to do this intersect test with AABB, each box or each AABB has a min X, min Y, and min Z, and a max X, max Y, and max Z. Okay? That's what it has. We also have some of this information from the mesh. All right? So, for example, when I go back to here, the mesh itself, the mesh renderer, what we have is a mesh that's connected to this thing called a cube, right? That's in the mesh filter. So if I wanted to get the extents of this object, right, as an example, I have a transform, but what things can we get from it just from code? Because we don't want to calculate stuff manually by hand. We don't want that. So is there a way of getting this information ahead of time instead of making your own class? So first of all, I have in the scripts folder, I have this cube behavior. All right. What I want to do is I want to take this cube behavior and attach it to, for now, just the green cube. So the way to do that is the player. I'm going to take the cube behavior script that I have. By the way, if you don't have cube behavior because you started a brand new thing, we can start. First of all, when you want to add a script, you want to right click and you want to go to create C# script. When you create a C# script, it'll create it and you can name it cube behavior. Once you name it cube behavior, if you double click onto it, it'll take you into your favorite editor. Mine is Visual Studio 2019, but yours can be Visual Studio Code if you want. And all I've done here is I've added a private void onDrawGizmos method, right? The onDrawGizmos method works. It's a built-in method to Unity, just like start and update. And what you can do is you can draw gizmos. Gizmos meaning little things. I'm going to draw a wire cube or a wire sphere if I want. These are examples of wire cubes and wire spheres, but let's do it from scratch. All right, since you guys may not have this stuff. You can also look online on my GitHub to get this code. But let's start it from scratch and see what this is. First, I need to attach this thing to the object. And the way to do that is if I click on the player object, once I have the script, I can just drag and drop it onto the component button, like this. The other way to do that is, if I detach it, I can detach it by removing my component, remove component. I can attach it by clicking add component and then selecting the name of the component by typing it in the search. So I can say cube behavior. That's also a way of doing it. And I can attach the same script to both objects, this object and this object. Okay? So for example, in the enemy object, I can just drag and drop the same cube behavior in there, and now both of them have these overlaps. Notice that the cube, I've added two things, a sphere gizmo as well as a cube wire gizmo. I don't need the sphere stuff, I'm just using this for demo purposes. So you can see that we can draw stuff in the editor, but in the game we'd see nothing. This is just for debug purposes that we're drawing these things. Let's go back into my cube behavior for a second. So let's get rid of this stuff altogether. I don't want a sphere. I'm just going to comment it out. And one thing we notice is that my color that I've chosen, you can make a color. So color gizmos, we can set the color for drawing the gizmos, right? And you can select a color like this, a custom color, or you can just select color dot, and there's a color class we can tap into, and we can choose a color that makes sense, that is a little bit different than what we have in our cube. Let's choose magenta, something like that. And if I don't specify what it is, and if I go back, you can see now when I go back here, if I refresh, that I have a magenta wire cube around both of those two things, and I've removed the gizmo for the sphere. All right. The magenta cube is the size of our object by default. Why? Because we've told it to be. We've said that draw wire cube size 1, 1, 1. That's the size of our cube. We want to replace this because if I change my cube, let's say I change my cube object, I go to my player, and inside of my cube, the scale of my cube, let's say I change it on the x-axis, I just can drag here. So I can go right next to any of these components here, x, y, and z on the scale of any object, and just drag it around, right? And you can see that my gizmo is showing a cube that's outside of my area, right? Why? Because my scale is off, right? I've changed my scale up. What we want is if I rescale my cube, I want my object to match, right? My scale. But there's many ways to do this. First of all, let's do a couple things. The first thing I want to do is I want to detect the size of my cube. So what we can do is we can tap into some parts of what we know. We know that each cube has a renderer. And the renderer has something called a cube mesh filter. Okay? Here's our mesh filter. So let's see what this we have to tap into this thing because now we have size 1, right? Sorry, here's our mesh filter right here, and the cube itself has some information for us. Let's see if we can get this information out of here. Let's see. And I'm being intuitive here. I'm not looking up online for documentation or anything like that yet. So the way to do that is to create a property that we can access. So when we access a script, and the script automatically attaches to our object, right? Just like how we did it. In Unity, the way it works is when we write scripts, each script, if it's part of mono behavior, should be attached to an object. But we don't have to do that. For now, let's assume that we do. We're going to make a public property, and the public property is going to be of type mesh filter. Here's our mesh filter. We're going to call this mesh filter. Whenever we make a public property in Unity inside of a script that's attached to an object, if I go back to the editor, you're going to see, if there's no errors, that the mesh filter is going to be attached here. There's two ways to get a reference to the mesh filter. One is to go here and drag and drop. Two, we can detect it automatically. And we can do that by going into my start and saying something like mesh filter is equal to get component. We're looking at the component that this script is attached to, right? Get component mesh filter. and then I can press semicolon. And this now has a reference. This mesh filter is a reference to the mesh filter that exists right here. It's looking inside of the game object, and it's saying, hey, game object, give me the first component that matches the thing that I'm looking for, which is mesh filter. That's what get component does. All right, so now I have a reference. This mesh filter is a reference to the mesh filter that's attached to my game object, this one. All right, cool. Let's see what we can do with it. Is this right? So if I type in mesh filter now, mesh filter dot mesh dot, well, there's some stuff I got. Here's one, bounds, right? Mesh filter dot mesh dot bounds. My friends, what does this give me? It gives me a bounds type. A bounds type. So this is a type we didn't know about. We don't even know what bounds is, right? But it's important to know what it gives us. Bounds dot center, bounds dot extents, bounds dot max, bounds dot min. You can totally use this, guys. This has nothing to do with physics. This has to do with the mesh. We're not doing 3D here. This is totally good to use. So if I say max, right, then I'm going to get what with it? If I hover over that, I'm getting a vector 3. Max, max x, max y, max z. I don't want to keep doing this every single time. This doesn't make any sense, right? X, y, and z. I don't want that, right? Instead, what I want, because bounds gives me a bunch of stuff. Bounds is a class that gives me a bunch of different things. Notice I have not just bounds, but also something else called extents, which is also a vector 3, okay? And it says the extents of the bounding box. This is great. This is always half of the size of the bounds, right? Which is kind of interesting. So this is kind of information that we get from this thing. We also have something called size. The total size of the box. This is always twice as large as the extents, all right? Which is also a vector 3. I would guess that vector 3 size, this vector 3 for size, is going to be something like a an object that is 111. That would be the size. Okay, let's do a couple things here, right? For bounds and size, right? First of all, we don't want to do mesh filter, mesh bounds. This is crazy, right? Instead, what I want to do is think about making another property, right? So if I say this time we'll make it private, we don't care to see it online, right? Or on in the editor. We'll make this private property, and we'll make the private property of type bounds. That's a type, right? And the bounds are going to be lowercase bounds. That's what we want to use, right? And what we want is to say that bounds is equal to mesh filter.mesh.bounds by itself, like this. So this is kind of our little alias. Bounds is our alias for everything else we have. Okay? Again, this is kind of information that we can share. This is going to give us some information for you. Tam says, technically we don't even need the mesh filter to be public since we get the component. Correct. I just wanted to show it to you. So when we run it, if I run this thing now, I'm not doing anything, right? If I run it, it'll automatically show the connection between the player mesh filter. That's why I made it public for you to see. And also, anything you make public appears here. So let's stop that. And like Tam said, we can make this private because we don't care about it. We don't care about showing that in the editor. Anything we make private, by default, does not appear here. Take a look. It goes away. However, if you want to see more defaults or debug information in here, even private variables, you can see them by right-clicking up here in the inspector and going to debug. Then we see everything, all the private variables, including the ones you defined. All right, so if I go to cube behavior, you can see that bounds and mesh filter are now there. Bounds is kind of an interesting thing to show though, right? Because look, it shows the center, 0, 0, 0, and the extent. And the same thing goes with my enemy, 0, 0, 0, and the extent. The extent is 0, 0, 0. That's kind of an interesting thing. When I run it, I can see those live. It shows me 0, 0, 0, and the extent is 0.5, 0.5, 0.5 away. This is the distance away from center. It also shows me the instance ID, which is sometimes it's important to know when we define one from the other. If I click on player, you can see again we have 0.5, 0.5, 0.5, 0.5. All right. Those are pretty cool things to know. So again, I did that by going to the inspector and right-clicking here and going on debug as opposed to normal. If I go to normal, it just says inspector. All right. So. If I go back in here now, if I have bounds, then I can show size, right? And size is actually a thing too, right? I have my transform. My transform tells me where I am. My size tells me how big my extents are, as an example, right? So let's go there and try that. So if I said I want a private size object, we'll call it size, right? And we don't want color size. We just want to do, well, actually, it doesn't really matter, right? But let's suppose if I did this, it brings up Unity system drawing. I'm fine with that. And color, I'm fine with that too. Sometimes it'll do extra usings as whatever's easier for it, right? So this is system.drawing.size is what I brought in, right? All right, cool. Well, I can always do something that looks like this. Let's make size public for us. So size is public. This is so we can expose it in the inspector. And let's go back down here and go size is equal to bounds.size. Let's do that. So, hey man, what happened? We have a size, but size is actually a vector 3. Let's change this to a vector 3. And let's get rid of this drawing stuff. We don't need the drawing stuff anymore. But size is something we want. So vector 3 is x, y, and z. We have, it's going to be size. We know that size is equal to size. I'm making little things here, bounds and size, so I don't have to go bounds.size. I don't have to go meshfilter.mesh.bounds. We don't have to do those things, right? Okay, let's go back to this, and let's see what we see in the inspector. We see a size of 0, 0, 0. Why? Because we're not running it yet. When we run it live, then for each object we touch, we're going to see a size of 1, 1, 1. What about if I change the scale? Will it automatically update? No. Why? Because size is only calculated once. In other words, unless we want it dynamically, the start function only triggers one time. The update function triggers every frame. So if I wanted for it to be dynamic, let's take this size function and drag and drop it into update. And then it'll update size every frame. Excuse me. I go back, and if I run it again, now it says 1, 1, 1, but if I'm clicking on player and I change the scale, right, then my expectation is that this would change, right? Size is equal to bounds, but somehow you can see that it doesn't change, right? Scale is kind of has nothing to do with the size of an object. All right, I'm just telling you what it is because the cube itself is a cube mesh. That's what it's giving us. So what can we're trying to get information about this thing, right? Doesn't really do anything. Even though every frame we're getting that, we're checking the size. Because it's not going to change. Size for the mesh is going to always be the same. The bounds for the mesh, well, that's different, right? Let's see if the bounds change. Or what about the max and the min? By the way, if you want to show stuff on the inspector, we can show it. It's easier to show on the inspector than show it in the debug in the console. The thing with the console is it gets cluttered very quickly, right? So let's add some other stuff in the inspector. We know that bounds can also supply us with other things. We don't have to make it in here. Let's put it one time. Let's put it here, back to this. What else can it give us? So bounds dot, like we said, max and min and extents. Let's see what we get with those two. We need to get an idea of what this is in order for us to make it work. Again, with max and min, it's a vector 3 object. So we're going to say size, public, vector 3, max, public, vector 3, min, right? Max and min. We're going to say that we're going to show what those are. So max is equal to bounds.max. Again, we're just exploring. And min is equal to bounds.min. All right, max and min. Cool. And we're going to see them appear here in the inspector, because anything that's public by default will appear as long as the data type is supported. It's going to appear here in the inspector. Let's try this out and see what happens. It's not showing anything. Have you dragged and dropped your script to the on the cube objects? Remember what I've done, Vanit, right? Control S, if you look here, you can see that this is all I've done, right? So a color that's magenta. I draw a wire cube that's around the object, right? Pretty simple. And inside my start method, we're just trying to explore what's happening with our bounds and our mesh. All right, let's go back to Unity for a second. All right, cool. So what do we get when I run it now? If I run it, and if I click on player, then I get this. I get max is 0.5, 0.5, 0.5. Min is minus 0.5, minus 0.5, minus 0.5. So that's how it does max and min. Cool. And if we take position into effect, 0, 0, 0, then we can kind of guesstimate where that's going to be. In this case, because of our green cube is in the center of the world, then the max and the min are accurate, right? Because the max is, if you look at it from a three-dimensional position perspective, right? If this is 0, 0, and if I go to the right, then to the right, 0.5, as an example, right, is where the max is, 0.5 to the right, okay? And then the next one is 0.5 up from the center. This is 0.5 from the center. So this 0, 0, 0 position is the center of the object, right? Call it the pivot or whatever. So this is from the center up, and from the center to the right, and from the center, and again, if you think about where the arrow points, right? That's why we're looking at it like this. This here, as an example in this case, if I move it this way, it goes negative. If I move it towards the arrow, it goes 0.5. So it means in this case that the positive or the max is right here, right? To the right, up, and this way. That's positive, which means the opposite is true for the negative, the minimum down here. That's the min, and that's the max. We have two objects or two points, and those 2 points are the things that we need, plus the position vector. So that way it's going to show the same thing. If I run on the enemy, right? Once I have the enemy running, here's my enemy, you can see that the numbers are the exact same, player and enemy. But we haven't taken into account the position vector. We need to do that. So let's do that now. So we're going to say that, going back to our code. Going back to our code, we're going to say that max is equal to bounds.max plus the position vector. Min is equal to bounds.min plus the position vector, transform.position, right? That's what, because really max is a vector 3. Let's add that in. So if I said, okay, well, let's add the position vector, I can say transform.position. Now, is this going to give us the right value? All right, and let's go to this plus transform.position. Well, for the cube, the first one, if I go back to Unity, right? Again, we're taking little baby steps here, so we're clear. If I go back to Unity now, and if I click on the player, then the player says that my max is 0.5, 0.5, 0.5, because nothing is adding into the position. All right. How about my enemy, though? Is this correct? My min is 0.83229 and 1.833. Right? 1.833. Why? 1.333 plus 0.5. Does this make sense? Of course it does. Why? Because this center is 1.333 away from the world origin, plus we're going to add 0.5 to it to give us our max. So this is our new max and min. Does it make sense? Yeah, I would agree, Tam. Vineet, maybe what's happened is you don't have a cube behavior attached to each of the cubes. If you don't have a cube behavior attached, then it won't show. Sorry. Tam, you have a question first? And then I'll go to Vineet. It's attached, okay? Vineet, maybe you want to stay after this, and I'll help you out. Okay. All right, now that we know this, we can apply the detection example, all right? So what we want to do is we want to make is colliding. We want to kind of create an is colliding Boolean that's going to appear here. All right, now because it's using the same script, we're going to detect if both are colliding. So we're going to make a new object. We're making it public so we can see it. And we're going to say the public is going to be something that is a Boolean, right? And it's going to be called is colliding. If I make it public in a Boolean, we get a checkbox inside the inspector, like this. Okay? What I want to do is when I move these things together, I want to detect if there's a collision. And we're going to use our code from here to do it, right? Now, there's a couple of things in order for us to do this, right? There's two ways we can do this. We can do it per cube, right? So each cube detects, or we can do it through some other main. For now, let's do it per cube. But we need to know the other cube. Each cube needs to know about the other one. So I need to know the other object I'm colliding with, okay, for now. So we need some kind of other game object that we can drag and drop in here, all right, to do that. So let's do that. First, we need to know the other object. So up in here where we have vector 3, size, max, min, underneath the is colliding, we'll leave the private ones down here, but we want to make another public game object, and we'll call it other cube. Okay, so size, max, min, game object, other cube. And when we go in there, other cube, I can find the other cube. But for now, all I want to do is go back in here, oops, and just drag and drop it in. How do I do that? If I'm in the player, then I want to get the enemy. If I'm in the enemy, I want to get the player. Let's do that. So in the player, I can drag and drop from the hierarchy into the other cube area, like so. Whoop. So the other cube is the enemy, right? Cool. What about the enemy? Well, the other cube is going to be the player. So I'm going to take the player and drag and drop it in. It's only checking for one thing at a time right now. Very, very simple collision detection. I want to pull this off, and then we're at least on our way to getting you to think about how things work. Now we're in play mode, so that won't hold. Let's try it again. So player, drag and drop the enemy, and enemy, drag and drop the player. We have one script we're using right now for both. Again, this is not the most efficient thing, but we're just trying to get you to think about how this all works. All right, let's move in. So I want to use this. A min is less than B max, and A max is greater than or equal to B min x, and so on. So I want to do this something down in here. So I want to say that I want to make a new something in update where when I'm running, I want to check collision between myself and other. So we can say that we'll call it check collision between myself and the other object, other cube. We don't have a check collision method. Let's make it private void. Actually, we'll make it void for now, because we'll just check on the stuff and check off. Private void check collision, and we'll pass in a game object that's called other. So every frame we're checking to see if we have a collision with the other object. Yeah, we can do that with tags. We can do a lot of things. But definitely we have to make something that checks collision with all the objects in the scene. In other words, what we'd rather do, Tim, is we want to look at all objects that are tagged a certain way, and then we can detect collision on all those objects, one object at a time, in some kind of loop. All right, so cool. Check collision, other. Let's try it out. Let's write that code. So we're going to write if A, let's suppose A is us, the main cube, min x. So let's do that. So we'll say, and again, I'm going to pull this aside just so I don't have to keep flipping back and forth. So I'm just going to take this and pull it on another monitor for myself, okay? So that way I can just type it and we're good to go. Otherwise, you guys are going to go back and forth and you're going to go crazy, right? So it's A, which is this, right? So this dot size, right? Now, how do I get the other's size, right? That's another weird thing. I want to get the other, right? The other, but do I really need for it to be a game object? What do I need from the other object? This is kind of a trick here with Unity. Because otherwise I'm going to have to do other.getComponent mesh filter and then bounds, and I'm going to need to get all this information right now, right? Somehow from the other. The only thing I need, right, if you think about it, is the max and the min from the other object. That's all I need. Max and min. Which means I need both max and min of the object somehow, right? Two vectors, max and min. So, or I can derive it, whatever you want. Because I can't get it in any other way. It doesn't know about the other cube. The other cube is just a regular game object. It doesn't know that it has a script on it, right? However, what I could do instead is, what if I need another game object with a script that is the same as mine, cube behavior. So if I did something like this, cube behavior, so another object with cube behavior as a script that's on it, right? Then if I go back to this isn't going to match anymore, right? So here as an example, I can't do other cube is this. It says that I'm getting an error. It says argument 1 cannot convert from cube behavior to Unity engine game object. That's absolutely true. So this would be no good anymore. This would be, it's an error that's causing me a problem. This would be cube behavior. So cube behavior. So another object of type cube behavior, which is what I really want. So now if I go back, I should see that this is other cube. I want to do it again. So enemy. So when I'm in the player, the enemy cube is the other cube. And when I'm in the enemy, the player cube is the other cube. Why did I do this? Because it saves me trouble. Because now other has all the properties of cube behavior. So I can say something like other dot and anything public as an example, like for example max, I have. Right? I couldn't have that before if it was just a game object. Also, just to make it so that it's really good, let's system.serializable up here. Let's put that little attribute up here, system.serializable. This makes it kind of available throughout our code. We're almost done, guys. Now, the detection. We're going to make a detection that says if our object min x, which min is min dot x, is less than or equal to the other, right? Min, right? Other dot min dot x, right? And just copying the thing, the other, sorry, this thing here. I'm just going to go to the next line here with our and. This dot max, right? max.x, max x, right, is greater than or equal to, this is back to what we did before, our other dot min dot x, right? Now, again, they've broken it down different ways. So this is kind of, I'm just breaking it down into this way. So they've done this. They've done min x is less than other dot max x, like this, sorry, it should be max x, other dot max x, and max x is greater than or equal to other dot min x, right? And, right? They're adding ands here, which is fine, right? Which means we have to have an extra bracket out here, right? And then we're going to say min dot y, right, is less than or equal to other dot max dot y, right? And max dot y, right, is greater than or equal to other dot min dot y. I'm just translating what I see in the PowerPoint slide. You should do the same. And let's put that so it's nicely proportional. And min dot z is less than or equal to other dot max dot z. You see where I'm going with this? The same thing over and over again. And max dot z, right, is greater than or equal to other dot min dot z, if I can spell other properly. And this is the check, guys. I'll put this up on GitHub later for you. If this is true, this check, then what we want to do is check on collision, which means our is colliding is going to be true. Else, just to make it simple, else, we could use a ternary operator here too, but just to make it simple, we're not going to do it. Is colliding is equal to false. There's our first collision detection method. Do you agree? System serializable allows us to share our, we serialize the entire class so we can use it outside of this file. So max x is like this max x, our object, right? Other is b. If you really don't like this, if you really want to be less confused, just refactor, rename to b, if that makes any sense here. There, that makes it easier for you. B max x, right? And max x is us, is a, right? And that's what this looks like. That's the formula. I'm just using the exact same formula from the slide, guys. No difference. All right, let's see if this works. So I've set this up just like this. I'll put this up on GitHub after. Let's see if this detects collision in real time. So going out to here, right? And if I run it, then do we get any errors? No, but I want to go here, right? And all I'm looking for is this is colliding to be true. So if I move this one into here, we should see what we're supposed to see, but we're not getting it. So why? Why is this happening? Right? This should be happening right now. I should be getting, each one of these things should be turning on, right? Right? But we're not. What's going on? How come it's not happening? Well, because it's not updating. Because when I move, this part here, this max bounds plus transform, is only doing it initially. It's not updating the max and the min every frame. It's got to be done down, not here, but rather in here. We need to update the position of the minimum and maximum every frame. That's what's going to happen. Let's try it again. All right, let's try it now. So run, go back into the scene, and if I drag one of them, we should get a collision now. Look at that. See how that check mark goes on and off? Yay! And it's pretty accurate. Look, I'm going really close, and it finds a collision, guys. Guys, once we do this and we have this kind of collision detection, we're golden. That means I can do collision detection between any two objects by doing a check, any kind of overlap, and immediately it tells us that we're colliding. We've made our own collision detection in 3D. Okay, on that, right, I can detect other things like floors, you know, whatever. And we also have to count the scale. We haven't taken into account the scale of an object either because we're using a mesh. Our mesh, we're assuming that the scale is 1, 1, 1. Right? 1, 1, 1 is going to change our min and maximums. Right? For example, in real time, if I change these, right, we don't have an overlap. Look at that. We don't have an overlap. Our bounding box remains this, like we said before. It doesn't change along with everything else. Right? If we want our bounding box to change, we need to adjust it according to the scale of our object. Okay, and this is the last thing we'll do. So, and by the way, are you with me? So all I've done is I've done a couple things here. Here's the code, so you can see it. All I've done is I've exposed size, max, and min is colliding as a little Boolean checkbox. We can check it. It's better than doing something on the debug log. Cube behavior is the other cube where it gives us more information than just a regular game object. Okay? And we're going to do something more special with cube behavior next time. We're going to make it so that it is a actor. We're going to call it something like an actor, which can apply to anything. Right? So our actor is going to have bounds. It's going to have additional things. Today, we don't have time for that. I'm just making it simple. Well, you can make your actor have as many things as you want that you can relate to other objects, right? But instead of calculating things by ourselves, we're getting the information from our mesh filter, which includes information about our mesh and our boundary. All right. So size, then, we're not really using, right? If you think about that, size is nice. But size is really the size of my object. My bounds, max, and min, in many ways are the things we want to modify, right? So our bounds then, which is a bounds object, right? It's really like we're taking our, the bounds and the size. Let's take a look at the difference between bounds and size. And I'm just going to expose bounds for 1 second. So if I go back to Unity, and if I want to right click here in the inspector and go debug, here's our debug. So this is what I'm looking for, and I'm running it in debug mode. I can see that my bounds are 0, 0, 0 for the center, and my extent is 0.5, 0.5, 0.5, right? And it doesn't matter whether I change my local scale or not. If I go to local scale, my transform, if I change my local scale to something bigger, this doesn't change, right? My bounds stays as is. This is the mesh bounds, right? So really, if you think about it, the max, which is 0.5, 0.5, 0.5, is the extents, right? That's really the size of my object, right? So there's a couple of approaches here, and then we'll stop for the day. Sorry guys, we're running a little bit longer than normal. There's a couple of approaches here. So how would you recommend, I'm going to go back to you guys now, because now I've done it. How would you recommend that I want to detect this scale? Right, so I have my local scale, transform. Remember, I can always go like this. I can say transform dot, and if I said scale, it gives me local scale. So transform.localscale.x.y.z. I can get those informations, right? So if my local scale of my object, and this is only if I'm using a cube, guys. This doesn't work if I'm using some other irregular object, all right? But if I'm using a cube and we were doing AAB type collision detection, can I modify my max by my scale? So if my max is really big, can I modify my bounds.max by my scale plus my transform position? And the answer is maybe I can. Let's try this out. So in real time, I want to say that I want to take my max and I want to multiply it by my scale and my min, and I want to multiply it by my local scale. So multiplied by my local scale. If it's 1, it's going to be the same. transform dot local scale, right? But here's something that happens, right? Max is a vector 3, and this is a vector 3, and my local scale seems to be a vector 3, and it says it cannot be applied. I can't say max times this. I can't multiply those two things together, right? It says cannot apply operand star to operands of type vector 3 and vector 3. That means it hasn't been overwritten. There isn't a thing like that to multiply, right, between the two. I need a little helper function to multiply. So we're going to make one. Private. We're going to call it multiply void. Actually, we're going to return a new vector 3 in this case. Right? Where we're going to say mult. That's what it's going to be called. I'm going to take two vectors, right? So a vector 3, which is going to be the left-hand side, and a vector 3 that's going to be the right-hand side. And what we're going to do is we're going to multiply them together, right? So we're going to say that we're going to make a new a vector 3 object. That's what we're going to make it. We're going to call it vector. And we're going to say that vector, right, dot x, make a new vector. Let's make it a new vector, is equal to a new vector 3 object. Sorry, I have to do this. We need to use the new keyword in C#. Vector dot x is equal to left-hand side dot x times right-hand side dot x, and we're gonna kind of copy paste this for all of them, since it can't do it. Y, and y, and I'm surprised it doesn't do it. I probably did something wrong, but that's okay, because I'm pretty sure they have this overload. All right, and return vector. Wonderful. So I made a new made a new little function, left-hand side, right-hand side. Take the left-hand side and multiply it by the right-hand side, and return as a new vector. Wonderful. Cool. I'm going to go back up here now and go, all right, I want my bounds to be multiplied. So I'm going to say mult bounds x max and transform local scale. And then I'm going to add my transform deposition. Again, shouldn't have to do this, but whatever. All right, let's see how this works, if it makes sense. One thing to note is that this isn't going to change either. So transform deposition is going to be, we're going to draw the cube, right, in the position of this thing, and then multiplied, the size is going to multiply by its, so we're going to say the same thing. We're going to say mult by a new vector 3 object, right? A new vector 3 object times, because right now it's 1, 1, 1. That's the scale, really the size or the extents, multiplied by local scale, transform dot local scale. So we can actually show the changes happening in real time. So that means that, let's try it locally first. So that means that if I modify my object in scale here, then we should have a shrinking magenta thing now. It's going to move with my object, right? Yeah, I could have done that, Tam. I'm just using mult. I made my own. I knew there was something I was doing wrong. Let's try it again. So if I go play, then we want to check what we have so far. So I can do this, right? No problem. It detects that I'm colliding. But what if I change the scale in real time? So if I do one of these and I say, well, my scale on my x-axis is going to change, right? In real time, take a look at my min and max. They change too. So now what we should be able to do is come closer and collide. So even if my scale is like this, it still works. And that's really what I wanted to show you today. Okay, that's just those little things. Again, if what Tam says is correct, we can dispense with this little function. Let's do the final version, which would be use vector3.scale. Let's try that out. Vector3.scale, right? And that makes more sense, and it's more something that's been built in that I'm not making, which is better. And I'll do the same thing down in here, vector3.scale. We can, by the way, dispense with this and get the actual size of the object, but that's okay. And we don't need this anymore, which kind of does the same thing. And I'm not putting a sphere on this right now. I just wanted to show you what it looked like, so that's what it is. And now we have kind of our final version of our code. Simple collision detection AABB, but all locked into these little Q behaviors. All right, so not good. What we want is a collision manager to take care of all this for us, a collision system, and we should be able to do collision detection and response now. Once we can decide, we can detect collision, right? What about if it's this way? It will still detect collision? Look at that, right? Or what about if it's up here, right? So we should be able to move it in real time, and we should still be able to detect collision, right? No matter what the point is. But one thing we cannot do is this simple collision detection does not take into account rotations. We are expecting everything to be axis aligned like this every single time. And for your assignment, that's okay. And notice that we are not colliding. It's very close, but we're not colliding. It looks like we are, but we're not until we do this. Then we are colliding. All right, any questions for any of this stuff? I'm going to stop recording now, and then I'm going to take questions. I'm going to put this up on GitHub. All right, so to put it up on GitHub, I'm